So in this next discussion, we have a chance to put everything together that we've talked about up to this point in time. We're going to call this our frame and packet forwarding process, but it's more than just that. But here we're going to really look at how it switches forward. We're going to really look at how routers forward, you're going to see everything that's going on, and we're going to put a whole story to it and follow along with the diagram and our real equipment. So with that in mind, let's go ahead and begin, folks. So, first question, when does layer 2 switching come into play? Right, layer 2 switching is going to come into play anytime we need to move our frames inside of our subnet, inside of our VLAN, inside of our broadcast domain. So in this particular case, for example, ASW1 is going to be responsible for layer 2 switching in our environment. Next question is, when does layer 3 routing come into play? Layer 3 routing is going to come into play anytime we want to move packets from one subnet, VLAN broadcast domain, to another subnet /VLAN /broadcast domain. So this multi-layer switch here is going to do layer 3 routing for us today. This router here, R2, is going to do layer 3 routing for us. The router on the internet is going to do layer 3 routing for us. Now, can this router do routing for us and this one too? Absolutely. But for our scenario, we're going to be focusing on these devices that you see right here, primarily, along with our PC and along with our web server that's hiding over here right now. So our story is this. You are sitting right here, right now. And you open your web browser. And you type in www.stormwindstudios.com in your web browser. And that is the server right here you are trying to reach. So what have you just triggered? Well, if you think about our previous discussion from yesterday and earlier today and everything that comes along with it, you have triggered your PC to start creating some data that then has to tie into the communications model. And it's going to have to go down and be encapsulated in a segment and a packet and a frame and then converted into bits and be sent out on the network. So right now, we'll use this as an HTTPS GET request. Get me, www.stormwindstudios.com. Now, because we're using TCP, we're going to need a TCP three-way handshake and a bunch of other things. We're not going to worry about that. All right, we're trying to understand the bigger picture here, okay, folks? So let's just focus on building our segment for our website, and let's not worry about all the other little things that happen to happen in regards to that as well, like doing the TCP three-way handshake. But when you think about your data, your HTTPS GET request, what are we going to have to do? We're going to have to send that into the communications model. We know we're using HTTPS, but now we have to do what? We have to pick our transport layer protocol. And so because it's HTTPS, our transport layer protocol is going to be TCP in this case. And we're going to need a source port and we're going to need a destination port, as well as many other things, but let's just focus on our source and destination port right now. So if you recall back from yesterday's discussion, our well-known ports are in that range, our registered ports are in that range, and our dynamic ports and private ports and ephemeral ports are in that final range. So can anybody tell me what the destination port number is going to be in this case? If this is HTTPS, going to www.stormwindstudios.com, that's right, it's 443. Make sure you remember that for the exam. It's probably going to show up in some way, shape, or form in some question. Okay, and where's the source port going to come from? Yeah, your computer's going to make it up from this range, right? Your computer's going to make it up from this range, right? So let's say it's 56537 for fun. 56537. All right, so we have our source port, we have our destination port. Obviously, there's going to be a sequence number in there. There's going to be the window size. There's going to be a whole bunch of other things. But let's not worry about all those little details right now. Let's get the bigger picture out of the way. All right, so we have our source and destination ports. PC1 source port 56537, and the web servers using 443. Now, why do I know the web server is using 443? Because that is what my web browser is pre-coded and pre-designed to use by default. If I don't want to use 443, then I have to manually define that in the URL as well, like I talked about yesterday. Okay, but typically we're using 443 for all HTTPS traffic out on the internet. All right, so now that we have our segment, right, let's go ahead and send this down to the network layer of the OSI model, the internet layer of the TCP/IP stack, and let's go ahead and start building our packet. Now, the two most important fields of our packet in this particular case is going to be our source and destination IP address. Yes, there's the QoS fields. Yes, there's the time to live field. Yes, there's the protocol field, right? We talked about those, but again, we're not going to worry about those for this discussion. But I do want to talk about the source and destination IP address because they are going to be really, really important. So the destination IP address, how do we get that? How do we get the destination IP address, folks? And how do we get the source IP address? Okay. Well, let's talk about the source IP address first. The source IP address we get from our local self, right? PC number 1 has an IP address that it got from what? DHCP probably. Maybe it was configured statically, probably not if it's a client, right? So from DHCP, so it got the IP address 10.0.0.10. So that's the source IP address that's going to go in there, right from its own configuration. Right? And then the destination IP address, as many of you have said, comes from DNS. Because you typed in www.stormwindstudios.com, our computer has to pause right now, and our computer has to reach out to the DNS server. It has to reach out to the DNS server. This is us. We're going to reach out to the DNS server and say, hey, who is stormwindstudios.com? I need their IP address. Now, if our local DNS server has the answer, then it's going to respond back to us. If it doesn't have the answer, then it's going to reach out to a higher level DNS server that it has the ability to talk to and find out if it knows the answer. Okay, in this case, the DNS servers have responded to us, and the answer is the web server stormwindstudios.com is at 192.0.2.5. 192.0.2.5. So now we know the destination IP address for www.stormwindstudios.com. So we have our source IP, which is PC1. We have the destination IP, which is our web server over here. We have our source port, which my client dynamically generated. We have the destination port, which is 443 for the web server. So now that we have our packet, let's move on down to build our frame at the next layer. Remember, PC1 is the one that's doing this right now. So it needs a source MAC address and a destination MAC address. So where does the source MAC address come from? Source MAC address comes from our own network interface card. So if we look at the output of IP config switch all, we're going to see that this is our MAC address. So we're going to be able to put our MAC address right up in there of 0011. It'll be the full MAC address, not just the last 4 digits, folks. Obviously, it's the whole MAC address. But for space savings, we're only going to put 4 in there. How do we get the destination MAC address now? How do we get the destination MAC address of the IP address we know about? ARP. ARP, 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 ARP. That's right. Okay, but we've got a problem here that I need to talk about now. We need to pause and learn a little bit more about ARP. Earlier today, we had a discussion on ARP during our frame forwarding process. And I said that PC5 needed the MAC address of PC2. You recall that discussion? So it's going to send out an ARP request. PC5 needs the MAC address of PC2. So it's going to send out an ARP request. So out on the network, it says, hey, if you're 10.0.0.20, give me your MAC address. Now, here's the thing. 10.0.0.20 was in the same subnet, same broadcast domain, same VLAN as PC5. So PC2 and PC5 are in the same subnet VLAN broadcast domain in that scenario. So that works perfectly. If the device you're trying to talk to is in the same subnet, same VLAN, same broadcast domain, then you ask for their MAC address. If they're not, you cannot do that. Look at this destination IP address. Is that in the same subnet, same VLAN, same broadcast domain as PC1? It's not. It's not. And if you're wondering, well, how do I know that? How do you know that, Raymond? Well, I can just look at these values down here and I can figure that out. Because I know just by looking at this that PC1 lives in the 10.0.0/24 network. And that would be from 10.0.0.0 to 10.0.0.255, just by looking at that. I can tell that. All right, I'll teach you how to do that tomorrow if you don't know how to do that. Right, so that IP address does not live in that range. So they're not in the same subnet. They're not in the same VLAN. They're not in the same broadcast. In addition, you can see that based on the diagram. Right, you're here, they're on the internet. Obviously, they're not in the same subnet VLAN broadcast domain. Okay, but mathematically, I can figure it out as well. So I can't ARP. I cannot ARP for this IP address. I can't do that. I cannot say, hey, if you're 192.0.2.5, give me your MAC address. That won't work. Because will the ARP request ever get to that web server? Nope. And why is that? Can anybody tell me why that ARP request would never get to that server? ARP is a broadcast, recall. And as Russ said, the broadcast domain ends at the router. Okay, so who is the router at the edge of this subnet VLAN broadcast domain? It's this one right here. It's my multi-layer switch. It's the default gateway. The default gateway for the 10.0.0.0/24 network. That's what that is. And if you're wondering a little bit more about my network here, this right here everything on this side of the line is my network. Everything on this side of the line is the internet. So this, though, is the default gateway for that network there. This is the default gateway for that little network there. This is my edge router going to the internet. There's another edge router going to the internet. So yeah, that's my default gateway for that subnet where that PC lives. You'll see here that the IP address of the default gateway is this. So the IP address of this default gateway is 10.0.0.254. What is a default gateway used for, folks? So first of all, as we said, the ARP broadcast will not go beyond the default gateway. It's contained within that subnet, contained within the VLAN, so it'll never get there. So what is a default gateway actually used for? Okay. A default gateway is going to be utilized as the entry and exit point of your subnet VLAN and broadcast domain. It's the entry and exit point of your subnet VLAN broadcast domain. So this is the entry exit point for my PCs that live down here. So if I want to send traffic out of my subnet, which I want to do, right? This is out of my subnet. Who do I have to send the frame to? Who do I have to send the frame to? It says router. Specifically, which router in this case? Yeah, the default gateway router. I got to send it to my default gateway. So wait a second. The frame is going from the PC to the default gateway in this scenario, but the packet is going from the PC to the web server? Yeah. Yeah. The only time the frame and the packet are going to the same device is if you are talking to somebody directly in your subnet VLAN broadcast domain. So for example, if PC1 was talking to PC2, then the destination IP address would be 10.0.0.20 as an example, and the destination MAC address would be PC2's MAC address. Because I could ARP for the MAC address of PC2, if that was the conversation that was going on. But since PC1 wants to talk to somebody outside the subnet VLAN broadcast domain, PC1's packet is sourced from itself, destined to the PC on the internet, the server on the internet, out of its subnet, and the frame is from PC1, destined to its default gateway. So in PC1's ARP cache, does it have a MAC address for 10.0.0.254, the IP address of the default gateway? And it does. 00000C07AC01. Now, if it didn't, what would PC1 do? PC1 would ARP for the MAC address of its default gateway. So DSW1 is its default gateway, folks, right there. There's the ARP request going. DSW1 gets it, goes, ooh, that's me. Let me respond back with my MAC address. And it's unicasted back to PC number 1. So watch that animation again in case you missed it. Right? So we got PC1 sending out its ARP request, gets flooded out all ports except the port it came in on, eventually gets to DSW1, and it says, ooh, that's me, and responds back with its MAC address. It's unicasted back to PC number 1, just like we talked about earlier today. But earlier today, we talked about 2 PCs doing that. Now it's the PC and the router. I need to determine the MAC address of this IP address, 10.0.0.254. I will send a broadcast ARP request to figure it out. PC2 gets it, goes, not me. I'm going to ignore this request. But the router says, that's me. I'm going to send a unicast ARP reply to PC1. Here's my MAC address. And that's your ARP. ARP in action. Very important to grasp these concepts, right, folks? Because it's imperative for you to be able to recognize on the exam too, right, how the frame is going to be built. If the 2 devices that want to talk to each other in the same subnet, same VLAN, same broadcast domain, then the IP will be the device in that broadcast domain. The destination MAC will be of that device. So you only ARP for the MAC address. You only ARP for the MAC address of this IP address if it's in the same subnet VLAN broadcast domain as you. If it's not, then you got to ARP for the MAC address of your default gateway. Let me repeat that. You only ARP for the MAC address of this IP address if that IP address is in the same subnet VLAN broadcast domain as you. But if it's not, then you ARP for the MAC address of your default gateway. How does your PC figure that out? How does it figure it out? It's actually a pretty simple process that requires a lot of binary 1s and 0s. It's called an ANDing process. You don't have to know this for the exam, but oftentimes I get the question, well, how does it do that? How does it even know? Well, I'll teach you that right now. I'm going to go to a different page because I don't want that info. I want this one right here. So I'm going to go back to this one. And what's going to happen is that you have the PC looks at its IP address, looks at its subnet mask, and it figures out its network ID. It's network ID in binary. So if we got 10 in binary, that's 00001010, and then you've got 00000000000000000, and then 000001010. Right, and then your subnet mask is gonna be 111111111 1111111 1111111. If you don't know where all these 1s and 0s are coming from, that's okay. I'll teach you tomorrow. You're gonna see all of these, how this all comes about tomorrow with these 1s and 0s. Okay, so that's that value there. That's that value there. Now, what the PC has to do is figure out its network ID. So the network ID is based on all these 1s, all these 1s, all these 1s, all these 1s, all these 1s. So the network ID is everything from here over to here. That's what it is. So there's the network ID. So now all it has to do is compare other devices' binary values to those ones that I have squared right there. So for example, this IP address, 192.0.2.5. So 192 in binary is what? 192 in binary is going to be 1 1 0 0 0 0 0 0, and then 0 1 2 3 4 5 6 7 8, and then you've got 2. So 0 0 0 0 0 0 1 0. Okay, and I'm going to stop right there because that is all we care about for network bits, right? Right up to there. So do these binary values match these binary values here? Do they match? The answer to that is no, they don't, right? They don't match. Because they don't match, PC1 knows that that IP address lives outside of the subnet VLAN broadcast domain, and therefore, what's PC1 going to do? ARP for the MAC address of its default gateway. Yep. All right. Now let's do an example where if it was PC2. So if it was PC2, let's say the IP address is 10.0.0.20. 10.0.0.20. So now 10.0.0.20 would be 0.0.0.0.10.1.0.1.0. 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8, and then 20 would be 0 0 0 16 0 1 0 0. Okay, well, again, this doesn't matter. At the end, it's just here. Do these right here match these right here? Yes, they do. They're the exact same. So PC1 now knows that who it's talking to is on the same subnet, therefore it'll ARP for the MAC address of that IP address. See the difference there? That's all. So your PC has the ability to do this and figure out, do I ARP for my default gateway or do I ARP for the MAC address of that particular device just by doing that math? Okay, so in this case, we ARP for the MAC address of our default gateway. So where are we looking at here? The frame is addressed to here, whereas the packet is addressed to here. The frame is going to the default gateway, but the packet is going to the web server. I know it's hard to wrap your head around that sometimes, but that's what's happening. And you're going to see it over and over again as we keep going here. Okay, so with that said now, let's take all of this, let's bundle it up, turn it into bits, and let's send it out on the network, folks. All right, so now ASW1 has received it. So the question is which of the values here, folks, will the switch use to make a forwarding decision? It's going to be the destination MAC address, as we talked about earlier today. So it's going to look at the destination MAC address and compare it to the MAC address table. So let's zoom in right now. And let's take a look at our MAC address table. We're looking for AC01. Do we have an AC01 in our MAC address table? We do. And which interface does it say we should exit out of? It says that we should exit out of gigabit 1/0/45. So that's this interface right here. So that's the way we are going to send our frame in this particular case. So that way there we can reach the default gateway. Now notice, the switch did nothing to the frame, right? It simply just forwards the frame. It doesn't change the frame, doesn't rewrite the frame, doesn't adjust anything. It looks at that information and makes a forwarding decision. So let's send it out at gigabit 1/0/45. And that's it. Our switch has done its job. Pretty straightforward, pretty simple. Now, DSW1 has received this frame. Now, DSW1 is a multi-layer switch, so it can do both frame forwarding as well as packet forwarding as well. So what's the first thing it's going to do in this particular case? The first thing it's going to do is take a look at that destination MAC address. That's what it's going to do. And when we look at this particular MAC address table on our device, we're going to see that on DSW1, that MAC address is statically set because it is a MAC address that's been assigned to a virtual interface on this particular router, on this particular multi-layer switch. So this device knows, hey, this frame belongs to me. It was sent to me. The frame was sent to me. So what does the multi-layer switch / router now do with that particular frame? Since the frame is destined to itself, it has to gobble it up. It has to use it. It has to consume it. It's gone. Now, that is the way it used to do it. It used to destroy the frame, gobble it up, and create a new one later on. Modern day equipment doesn't do that. Modern day equipment leaves the structure of the frame there and simply rewrites the values that it needs to rewrite. Doesn't make sense to rebuild something if you don't have to, right? If the construct is already there, the fields are already there, and all you have to do is erase something and change a value in it, then that's what you're going to do in modern day equipment. But for the sake of learning, we're going to gobble things up and destroy them and recreate them like we used to do in the past. Right? So now that the frame, that the router determined that the frame belonged to itself, now what it does is it looks at the destination IP address and it says, does this belong to me? Well, what is it going to use to determine that? It's going to have to use its routing table. So if we go to DSW1 and we type in show IP route, we're looking for 192.0.2.5. If we start going through this list, we'll see that this doesn't match, this doesn't match, this doesn't match, this doesn't match, this doesn't match. No, 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 no. There you go. That one does match. That one does match. So we're going to have to use the default route in this particular case. So now what does the device have to do? Well, the device has to figure out which interface it's going to have to send this out of. So it looks at the routing table to figure that out, and it says, oh, I've got to send it out gigabit Ethernet 1/0/14, which is this interface right here. And the next router along the path, so there's some router down here, somewhere down here, with the IP address 10.40.23.5. So I'm going to send it out gigabit 1/0/14 to the next hop router of 10.40.23.5. So because this is an Ethernet interface, what does the router have to do now, folks? What does the router have to do to this packet? Can I just send a packet out an interface? Can I just send a packet out an Ethernet interface? Or do I have to do something to it first? We need to frame it, right? We need to frame it, encapsulate it in a frame. Exactly. Exactly. Just like the PC did, remember? The PC took the packet, turned it into a frame, then sent it out as bits on the wire. Well, right now I'm at the packet. There's no frame anymore. So the router, you notice how the router got rid of the frame, used the packet information, now it's got to rebuild our frame for us. Now, again, on modern day equipment, are we destroying the frame? No. But the router would have to rewrite all the framing information. Rewrite the framing information. So it makes sense for this next leg of the journey. Remember how yesterday I said MAC addresses are only used in your subnet, in your VLAN, in your broadcast domain? Well, this was one subnet VLAN broadcast domain over here, right? It's where my PCs lived. Well, this is technically another subnet / VLAN / broadcast domain right here. It is. Absolutely. And so we need a source and a destination MAC address to transport the frame through that part of the network now. Earlier today, somebody says, Raymond, are you telling me that the frames are going to change? The MAC addresses are going to change? Yes, you're seeing it now. You're seeing it now. This is it. So how do we figure out the source and destination MAC address? Well, the MAC address of this interface is going to be the source, and the MAC address of this IP address is going to be the destination. Source MAC, destination MAC. Source MAC, destination MAC. So I need the source MAC address of this, and I need the MAC address of that. I need the MAC of this for the source. I need the MAC of that for the destination. So let's type in show interface, gigabit Ethernet 1/0/14. There's the MAC address. 9643. And now let's type in show IP ARP to see the ARP cache on the router. And what IP address are we looking for? 1040.23.5. There it is. So at some point in time, my router did an ARP request for the MAC address of that IP address. And there we go. We got it. So 6388. 6388. There's our two values. So now we can go ahead and build that frame. All right, so there it is. 9642 6388. So now these have not changed at all. They're still the same, but these are now new. Source here, destination somewhere down here. Let's go ahead and watch this move now. Here you go. Right, so now R2 has received the frame. Looks at the destination MAC address. We type in show interface gigabit Ethernet 0/0 because that's the interface it came in on. That's the MAC address. So now R2 knows that this frame belongs to itself. It knows that. So what's it going to do? Gobble up the frame because the frame belongs to it. The frame was destined to the router. So now the router looks at what? Looks at the destination IP address and says, does this belong to me? So we type in show IP route again. And the router goes through its entire list of things. 192, what are we looking for? 192.02.5. And when I look at all these options, this doesn't match, doesn't match. Now you might say, ooh, this one matches. No, I know it's 192.02, but we're looking for 2.5, and this is 240 and 242. That's not going to work. And you might say, oh, that entry is no. That is like an index. It's like a header. Sorry, a header. Right? Notice how the 10 network is split here. It says the following entries belong to the 10 network. The following entries belong to 172.16. The following entries, that's all that is. It's telling you that the following networks belong to this classful subnet. That's all it means. Think of it as like a header for the addresses that are below it. So that doesn't apply. That doesn't apply. So we keep going. There's nothing. So we're back to this entry right here. So this is the entry that matches in this scenario. And it says via 203.01.13.89. And notice there's no interface in this scenario. And I did this on purpose so I can teach you something else. So when the router doesn't know the exiting interface, what does it have to do? It has to figure it out. It has to do what we call a recursive lookup. A recursive lookup. So all a recursive lookup is the router doing another routing table lookup. Another routing table lookup. So what the router does is it says, okay, so I know that I got to use this entry here, and I know I have to go via 203.01.13.89. But the question is how do I get to 203.01.13.89? So it looks down through its routing table, and it finds an entry that will get it to this address right here. So in our case, it's this entry right here. That would work for us. That IP address lives within that network. Therefore, our exiting interface is fast Ethernet 00. So we're going to go fast Ethernet 0/0/0. And the destination is someone over here called 203 10.0.113.89. Ran out of space. 89. That's what we're doing. So there's our exiting interface. There's our next hop. So this is going to be a source MAC. And this is going to be the destination MAC. So how do we get that source MAC? Well, it's baked into our interface. So we'll type in the command here momentarily, show interface, fast Ethernet 0 size 0 size 0. We'll be able to see the MAC address there. So remember, the router does this all by itself, right? You don't have to do any of this. It's taking care of it all for you. Right, and you'll see that the MAC address ends in ACD4. So I'll just type that in right now, ACD4. And then when we want to look at the MAC address of the destination of 203.0.113.89, show IPR. And so we've already gotten it from some previous ARP request. If not, we would have to send out an ARP request. 03D3 are the final 4 digits. I'll write those down. 03D3. There you go. So now we have that information. We're going to be able to build our frame. But wait a second. Before we can go ahead and build that frame, there's something else that we have to take into consideration here. And that is the fact that we are going out to the internet, aren't we? We are leaving and we're going to the internet. Is this IP address allowed on the internet, folks? Nope. It's a private IP address. RFC 1918 private IP address. So it's not allowed on the internet. So what are we going to have to do? We would, on this router, be running network address translation. That's what we'd be doing, network address translation. Specifically port address translation. But I'm not going to teach you about that now. We're going to learn about it in a future session here. Next week, we'll learn about it. But network address translation is going to have to translate this to a public IP address from an approved list of public IP addresses that we've set up for network address translation. So let's just go ahead and do that right now to make it as realistic as possible. So the source IP changed to an IP address that is approved with network address translation. That's how that and there's a table here that's going to be kept. The table is going to say 10.0.0.10 has been translated to 203.0.113.91, and we're going to a destination of 192.0.2.5. So that way when the traffic is coming back, this entry can be used to convert it back to what it needs to be converted back to. Right, so that's what NAT would be doing for us to get out on the internet. Okay, so let's go ahead and build our frame now that we've changed the source IP. So there's the source and destination MAC address that we had. We can then package it all up, bid it up, and send it out on the network. Okay, folks, and this is going to happen over and over and over and over again. All the way. All the way. So this frame belonged to the router, did a routing table lookup, figured out what the destination IP address is. So then what it's going to do is it's going to go ahead and figure out what exiting interface. It's going to figure out what the new source and destination MAC address has to be for the next leg of the journey, put it in, and away it goes. Over and over and over again. So every router is going to have to do this. So let's just say for fun, we've gone through let's say you've gone through 20 routers, just 20 routers. And now you finally reached the very last router in the journey. And that is the data center router. The data center router that's hosting www.stormwindstudios.com. Remember, that's where you're going. You remember you typed that in 38 minutes ago. 38 minutes ago, and you're still waiting for the results to show up on your screen. All right, so the last router along the path, right, received the frame, looks at the destination, oh, that's my destination MAC address. So what's it going to do? It's going to rip off the frame, just like we've talked about. Now it looks at the destination IP. The crazy thing here is that the IP address of this interface might be something like 192.0.2.1. What does that mean? It means that this interface is in the same subnet as the web server. So what does that mean? It means that this router can ARP for MAC address of the actual destination IP address now. So when you are directly connected to the destination IP address, you can ARP for the MAC address of that destination IP address if you're a router. So that's what this router is going to do. It's going to ARP for the MAC address of that web server. And it's going to get the response back for it. And it's going to go ahead and build its frame. And it knows that it has to send out this interface because it's directly connected to the same network of that IP address. So the routing table would have shown a directly connected route, like we saw earlier in today's session when we talked about routing, and package it all up. Once the frame is built, sent it out on the network. The data center switch here that we have, let's say, is a layer 2 switch. And then it's just going to look at the destination MAC address and say, oh, that's that way. So I'm going to go ahead and package it back up and send it out that way. And then the web server gets it. Whew, that was a long journey. But now it gets there, and the web server says, is this my destination MAC address? Oh, yes, it is. Great. Is this my IP address? Oh, yes, it is. Am I listening on port 443? Oh, yes, I am. What is this? Oh, it's an HTTPS message. Let's send it to my web server application. Right? And then it's going to get, it was you typing in stormwindstudios.com, so it was an HTTPS GET request, get me the index.html file, get me the page for stormwindstudios.com. So what does that mean? It means now the web server has to respond back to you. So it's going to have to respond back with the web page or the information to get everything you need for that web page. Right? And now look at the port numbers. They're reversed. You see that? Because the source is now the web server and the destination is you way over there. They're reversed. You see that? So everything's in reverse now. IP addresses, reverse. And the MAC addresses would be in reverse as well. But in this case, the source and destination MAC addresses are what? Source MAC is the web server. Destination MAC address is its default gateway. So same thing that we talked about before coming from our PC. Now we're just doing everything in reverse. So again, it's going to happen. I'm not going to bore you. Because it's the same thing over and over and over again that we already talked about. All right, so eventually the ISP router here that is connected to us is going to get it. So let's say it was some, it's already gone through maybe 16 hops to get back to us. So that is the MAC address. The destination MAC address is that of the ISP. So the ISP, again, would gobble that up. Look at the destination IP and say, oh, based on my routing table, I got to send it this way. This is going to be the exit interface. It's going to be a next hop IP address of 203.0.113, whatever. Right? And then what it's going to do is it's going to go ahead and build a new frame to get it down to my router R number 2. All right. So we get back here now to R number 2. And R number 2, it arrived in on fast Ethernet 0/0/0. So R number 2, if we go to that and we type in show interface fast Ethernet, oh, it was 0/0/0. It came in on, right? So MAC address ACD4. And you'll see here that the MAC address is ACD4. Arrived in on fast Ethernet 0/0/0. Okay, so the router knows it belongs to itself, so it takes it off. Now, it looks at the destination IP, and it realizes that that is one of its network address translation IP addresses, right? So it's going to look at its network address translation table. And when it looks at the network address translation table, it's going to see that 10.0.0.10 was translated to 203.0.113.91, and that traffic was destined to 192.0.2.5. So this matches this, that matches that, so that means this has to be translated back to that. So the router's going to do that first. It translates it back, and now that it's translated back, it can go ahead and do its routing table lookup now. So now it does its routing table lookup. So NAT has to be done first on the way back, then routing. We're on the way out. Routing was first, NAT was second. And we'll see here that we're trying to get to this network right here. 10.0.0.0/24, because the destination is what? 10.0.0.10. 10.0.0.10 lives in 10.0.0.24. So it says that we're going out gigabit Ethernet 0/0 with an X-top IP address of 10.40.23.6. So MAC address, source, MAC address, destination. So those values, just like we saw before, if I just type in show IP ARP here, we'll actually see both of them. We'll see that the source MAC is going to be 6388, and the destination MAC is going to be 9643. So we can go ahead and put those in. Oh, I got a typo there. It should be 9643, not 9642, but that's okay. I have a typo in my slide. Okay, so package that all back up, send it across. Gets the other side, DSW1 gets it, looks at the destination MAC address. Ooh, that one is wrong there. That one is wrong. So what happens sometimes when devices get changed in your demo environment? That should be 9643. 9643. So let's take a peek at that on that router. So if we go over to DSW1, we type in show interface gigabit Ethernet 1/0/14. There it is right there, 9643. So it knows that the frame belongs to itself. So what you're going to do, like we talked about before, destroy it. Oh, there, it did change. So it must be an issue. I saw a little flash there. You see that little flash? It changed it to the right one. So there's something wrong with the animation of the slide. It's showing an old one as opposed to a new one. There you go. I'll get that fixed. All right, so now that we've destroyed the frame, we can go ahead and we can look at the packet itself. So 10.0.0.10. So the router can go ahead and do a routing table lookup now. Show IP route. And we'll see that 10.0.0.10 would fall into this. Notice it's directly connected. Directly connected to interface VLAN 1. Interface VLAN 1. All right, so 10.0.0/24 is the network that the PC lives on. Directly connected to VLAN 1. So what does that mean when it's directly connected? It means we can ARP for the MAC address of the PC of 10.0.0.10. Anytime you see directly connected, it means you can ARP for the MAC address of that value. Okay, it means you're on the same subnet. It means you're on the same VLAN. So if I just type in show IP ARP here right now, you're going to see my router knows the client. There it is. The router knows the client. So anytime you have directly connected, the router will know that client that lives in that subnet VLAN broadcast domain. So now we know the MAC address for PC1 is 080027880011. So we can go ahead and put that in our frame. And then our interface of VLAN 1 would have a MAC address in this case of AC01. So I just put that in. And then we can now go ahead and package it all up, ship it down to ASW1 on the way back. And when ASW1 gets it, it's going to do its MAC address table lookup. And it's going to be looking up the destination of 0011, which is PC1. Oops. Timeout. It timed out. Why? Because PC1 went into sleep mode on me, and we haven't been using it in a while. So there we go, 0011. So remember, because it didn't know about it, what would it do? It would flood it out all ports except the port it came in on, right? Unknown unicast frame flooded out all ports except the port it came in on. Known unicast frame forwarded out the specific port. So keep that in mind for the exam too. Even though 0011 wasn't in the MAC address table, the ASW1 would have still flooded it out all ports except the port it came in on to get it there. Unknown unicast frame, like we talked about earlier today. All right, so now we got populated table, so it would forward it instead of flooding it. All right, but just giving you examples, just showing you things that can happen, right? And being able to address those on the exam is important.